Welcome to the third and final part of our lesson on stereoisomerism, where we will focus on optical activity. In this section, we'll explore the concept of plane polarized light and how it interacts with chiral molecules. We will learn how to measure optical activity using a polarimeter, understand the symbols and notation used to describe optical rotation, and finally, discuss racemic mixtures. Let's get started on the next page with a brief overview of optical activity. Optical activity is an observable property that allows us to distinguish between enantiomers. Even though enantiomers, such as R-carvone and S-carvone, have identical physical properties like melting points and boiling points, they exhibit unique behaviors in two significant ways. First, they interact differently with other chiral compounds, which can lead to varied biological and chemical activities. Second, they differ in their optical activity, meaning they rotate a special form of light called plane polarized light. We will discuss plane polarized light shortly. For now, know that when plane polarized light passes through a solution containing one enantiomer, it will rotate the light in a specific direction, either to the right, dextrorotatory, or to the left, levorotatory. The direction and amount it rotates the light are intrinsic to the compound. A single enantiomer will always rotate light in the same direction and to the same degree. This rotation is measurable and helps us distinguish between enantiomers. To fully understand optical activity, we need to grasp the concept of plane polarized light and its interaction with chiral compounds. Let's transition to the next page, where we will briefly review the wave nature of light, setting the stage for our discussion on light that has been polarized in a single plane. To understand how enantiomers affect light, we need to grasp the basics of electromagnetic waves. Electromagnetic waves, such as light, have oscillations in both the electric and magnetic fields as they propagate through spacetime. As illustrated on the slide, the electric field oscillates in one plane, while the magnetic field oscillates in a plane perpendicular to the electric field. These fields are interdependent and propagate together as a wave. When light interacts with enantiomers, it encounters these oscillating electric and magnetic fields. Enantiomers have unique three-dimensional structures that cause them to interact with the electric field component of the light wave in a specific manner. This interaction leads to a rotation of the plane of oscillation of the light. The direction of this rotation depends on the specific enantiomer. One enantiomer will rotate the light to the right, dextrorotatory, while the other enantiomer will rotate it to the left, levorotatory. This rotation of light by enantiomers is what we refer to as optical activity. It is a distinctive property that helps us distinguish between different enantiomers based on how they interact with light. Next, let's move on to the next slide, where we will explore the concept of plane polarized light in more detail and understand its significance in the context of optical activity. Plane polarized light is light that oscillates in only one plane. Normally, light waves oscillate in multiple planes, with electric and magnetic fields vibrating in various directions perpendicular to the direction of the light's travel. When light is unpolarized, these vibrations occur in all possible directions perpendicular to the light's path. To understand the optical properties of chiral compounds, we need to use plane polarized light. Plane polarized light is crucial because it allows us to observe how chiral molecules interact with light, specifically how they rotate the plane of polarization. This rotation, called optical activity, is a key property that helps us distinguish between enantiomers. So, how do we create plane polarized light? It begins with unpolarized light, which consists of waves oscillating in multiple planes, perpendicular to the direction of propagation. To convert this into plane polarized light, we pass it through a device known as a polarization filter. This filter selectively allows only the light waves oscillating in a single plane to pass through, while blocking all other orientations. As a result, the transmitted light has its electric field oscillating in just one plane, and we call this plane polarized light. Polarized light has many practical applications. For instance, polarized sunglasses use this principle to reduce glare. They contain materials that filter light, allowing only vertically polarized light to pass through, and blocking the horizontally polarized light, often reflected from surfaces like water or roads. In the realm of chemistry, especially in studying chiral molecules, we use an instrument called a polarimeter. A polarimeter measures the angle by which a chiral compound rotates the plane of polarized light. By analyzing this rotation, we can gain insights into the properties of the chiral compound and distinguish between its enantiomers. Let's move on to see how a polarimeter works and how it helps us understand the optical activity of chiral compounds. To measure optical rotation, we use an instrument called a polarimeter. A polarimeter helps us determine both the degree and direction of rotation caused by a chiral compound when plane polarized light passes through a sample of the compound. Let's walk through the components and process of using a polarimeter. The polarimeter begins with a light source, typically a sodium lamp that emits light at a specific wavelength, such as the D line of sodium. This light passes through a polarizer, which is a filter that only allows light waves oscillating in a single plane to pass through. This creates plane polarized light. Next, the plane polarized light enters the sample tube, which contains a solution of the chiral compound. As the plane polarized light travels through the chiral solution, the molecules interact with the light's electric field, causing the plane of polarization to rotate. The amount and direction of this rotation depend on the nature of the chiral compound. After passing through the sample tube, the rotated light encounters another polarizing filter, called the analyzer. The analyzer can be rotated to measure the angle at which the light passes through it with maximum intensity. This angle corresponds to the degree of rotation induced by the chiral compound. The observer or detector then reads the angle of rotation on a degree scale, which is usually fixed in the polarimeter. The rotation can either be to the right, known as dextrorotatory, or to the left, known as levorotatory. By using a polarimeter, chemists can accurately measure the optical rotation of chiral compounds, allowing them to distinguish between enantiomers and determine their purity and concentration. Understanding this process is crucial in fields such as pharmaceuticals, where the optical activity of compounds can significantly impact their effectiveness and safety. Now, let's move to the next page and learn about how optical rotation data is expressed and how it is interpreted. Let's discuss the symbols and concepts related to optical rotation. When we measure the optical rotation of enantiomers, we observe that they rotate the plane of polarized light to equal degrees, but in opposite directions. The degree to which the light is rotated depends on two main factors: the concentration of the sample and the path length of the light through the solution. Standard optical rotation measurements are typically conducted with a solution containing 1 gram of the compound dissolved in 1 milliliter of solvent, and using a path length of 1 decimeter for the light. These conditions are used to ensure consistency and comparability of results across different experiments and compounds. Additionally, it's important to note that both the temperature and the wavelength of light can affect the observed optical rotation. Therefore, when reporting measurements, it's essential to include the specific temperature and wavelength at which the measurements were taken. The specific rotation is a standardized way of expressing optical rotation, and is calculated by taking the observed rotation, alpha, and dividing it by the product of the concentration, C, of the solution, and the path length, L, of the light. This relationship allows for the comparison of optical rotations of different compounds under standardized conditions. Let's go to the next page and see an example for how these symbols are used to express optical activity for a sample of a chiral compound. To understand how optical rotation symbols are used, Let's look at the stereoisomers of 2-bromobutane. On this slide, we see the two enantiomers, R2-bromobutane and S2-bromobutane. The R and S designations refer to the absolute configuration of the chiral center in each molecule, determined using the priority rules. For R2-bromobutane, the observed optical rotation is negative 23.1 degrees. The negative sign indicates that this enantiomer rotates planed polarized light to the left, a property known as levorotatory. On the other hand, S2-bromobutane has an observed optical rotation of positive 23.1 degrees. The positive sign indicates that this enantiomer rotates plane polarized light to the right, a property known as dextrorotatory. These values of optical rotation are measured under specific conditions, indicated by the notation 20 and D. The 20 represents the temperature at which the measurement was taken, 20 degrees Celsius, and the D refers to the wavelength of the light used, the sodium D line at 589 nanometers. By comparing these values, we can see that enantiomers rotate plane polarized light to equal extents, but in opposite directions. Another important note is that there is no correlation between the direction which a molecule will rotate plane polarized light and the absolute configuration of its chiral centers. In other words, the R and S configurations on a molecule have no bearing on if the molecule will be dextrorotatory or levorotatory. An experiment is necessary to establish the optical rotation. Now that we have discussed how chiral compounds and enantiomers can be differentiated by their optical activity, let's move on to the final topic of the lesson: racemic mixtures. Let's conclude the lesson with a brief discussion of a situation we frequently encounter in the practical application of organic chemistry, specifically, racemic mixtures. In the absence of a chiral environment, most reactions will produce a 50-50 mixture of both enantiomers when a new chiral center is generated. This happens because there is no preference or bias towards the formation of one enantiomer over the other in a symmetric, achiral environment. The reaction pathway is equally probable for the creation of both the right-handed and left-handed enantiomers, leading to a mixture where equal amounts of both enantiomers are present. These mixtures, known as racemic mixtures, have an optical rotation of 0 degrees. This means they do not rotate plane polarized light, as the equal and opposite rotations of the two enantiomers cancel each other out. For example, if we have a reaction that produces equal amounts of R2-butanol and S2-butanol, such as when we perform the hydration of 2-butene with water and an acid catalyst, the mixture will be racemic. Because each enantiomer rotates plane polarized light in equal but opposite directions, the overall effect is no rotation. In contrast, a chiral environment can induce the formation of a single enantiomer, leading to enantiomerically enriched or pure products. This is because a chiral environment provides an asymmetric influence on the reaction, favoring the formation of one enantiomer over the other. This can happen through several mechanisms, including chiral catalysis, chiral solvents and ligands, and chiral induction by the presence of asymmetry on molecules in the reaction environment. Chemists frequently utilize natural sources of chiral materials, instead of synthetic ones, because the enzymes in living systems are inherently chiral. These enzymes impart chirality to the compounds produced by these organisms, a concept commonly known as the chiral pool. This concludes our lesson on stereoisomerism. I hope you found the information helpful and engaging. If you have any questions or need further clarification, feel free to reach out. Thanks for following along, and see you in the next lesson.